This video recording is one in the series commemorating the discovery of a particle that scientists call the Higgs boson. This video is going to highlight the difficulty that the scientists had in making this discovery, and it's going to commemorate what a tremendous achievement it was that we were able to discover the Higgs boson. Now, back on the 4th of July in 2012, the team that was running the ATLAS experiment announced that they were 95% confident that they had found the Higgs boson. Now, they started this experiment back in 2008. They've been running this experiment for years, and in order to discover the Higgs boson, they had to smash particles together at an extremely fast rate to collect enough data. They were having 40 million to 100 million smashes per second in their instrument, the Large Hadron Collider in Geneva, Switzerland, in order to collect enough data, and this had to go on for years. Now, why was it so difficult, and why did they have to run so many experiments? Well, what they faced was a typical problem that scientists and engineers face, and even every person faces, and it has relevance for each and every one of us, and I want to discuss that. What they faced was a signal-to-noise problem. The signal that they were looking for was very, very weak, and the noise that the signal was embedded in was extremely high. Let me show you an example of a signal, a very clean signal. This signal is something that mathematicians would call a sine wave. It's smooth and pretty and very predictable. If you were to keep going with this, you would know at every point along the way pretty much what it would look like. And this is what it would sound like. Now, this is a typical example of noise. It's chaotic and it's unpredictable. If you were to keep going with this noise and carry it out, you wouldn't know at any given point how far above or below the center line the signal was going to be. Here's what this particular noise would sound like. Now let's do a little thought experiment. Let's say you're standing in a room, and right next to you is Harry S. Truman. And he's practicing his famous speech where he tells the American people that the atomic bomb has been dropped on Hiroshima. Now, here's what Harry would sound like. And I'm going to show an image of the clean signal sine wave so that gets the point across that this signal is very clean. You're hearing Harry very clearly.
The first atomic bomb was dropped on Hiroshima, a military base.
Now suppose President Truman is still next to you and he continues to practice his speech, but somebody in the apartment next door is operating a power saw. Here's what it would sound like.
The first atomic bomb was dropped on Hiroshima, a military base.
And here's an image representing what we would hear. There's our signal. In this case, it's the sine wave. And there's some noise superposed on top of the signal. But you can still hear Harry fairly well, and you can still see quite a bit of the sine wave. It's just noisy. Now let's change things around still further. Let's say Harry Truman is in the apartment next door practicing his speech, and you're in the same room with the person operating the power saw. Now here's what it would sound like.
The first atomic bomb was dropped on Hiroshima, a military base.
And again, here's what it would look like. There's our sine wave, but it's buried under quite a bit of noise. In fact, it's a little bit hard to make out the sine wave, but it's there. But we're seeing a lot of noise. And that represents what we heard. We could make out Harry Truman's voice, but it was buried under a lot of noise. Now let's take things to extremes. Let's say Harry Truman is 3 doors down. And let's say you're in the room with the person operating the power saw. Pretty much all you would hear is the power saw. Harry Truman's voice is way too faint to make out. And here's a picture representing that situation where our sine wave is buried under a lot of noise. You can't even make out the sine wave. You couldn't even be sure that it's there. The signal is very, very weak, and the noise from the saw is very strong. For all intents and purposes, the signal is gone. Now, this is what scientists and engineers call a very low signal-to-noise ratio. And this isn't just an academic example. This can affect you in your real life. This is something we face every day as we try to figure out what's going on in a world where kind of chaotic things are happening. Let's say, for example, you're reading a magazine article, and it says that if you're feeling run down, you might be helped by taking more folic acid. So you go to the drugstore, and you buy a bottle of folic acid, and you start taking it. Now, how do you know it's working? How do you know it's effective? Well, what you might want to do is just see, do I feel better? Do I have more energy? But this isn't an easy thing to do. You might one day feel less energetic, but that's because you mowed the lawn and trimmed the bushes in the hot sun. I mean, the next day you might be feeling more energy, but that might be because you had a lot of coffee. The noise is great, and the signal might be kind of weak. That's why experiments of that sort are very difficult to make on a personal level. Well, there's a way to deal with this problem, at least if you're an engineer or a scientist, and that is to collect a lot of data, to collect the same signals over and over again. What you can do is combine these signals mathematically. And when you do that, what happens is the signal starts to increase because it's pretty much the same from experiment to experiment, or at least that's what you're looking for. And the noise is not. The noise is chaotic. And when you combine these mathematically, you start to see the signal emerge, and the noise doesn't reinforce itself. Well, this is what the scientists at CERN running the ATLAS experiment had to do. They had to collect a lot of data. Engineers do this routinely in communications. You might have a really weak signal coming from somewhere. We send satellites way out into space, and we expect to get decent pictures and images. How do we do that? I mean, you can be driving away from your city, and you're listening to your favorite radio station. Now, that station might have a 50,000 watt transmitter, and when you get about 40 or 50 miles away from that station, it starts to get pretty weak. I mean, if you're going down a hill and the station's on the other side, you can sometimes barely hear your music over the noise. Now, think what would happen if you sent a satellite 100 million miles away from you into space, and it doesn't have a whole lot in the way of a battery or a photocell. Your transmitter, if you have 3 watts, you're lucky. Well, this signal is just buried in a ton of noise. It looks very much like Harry Truman with the 3 doors away with the power saw blasting right next to your ear. The way scientists do this, or communications engineers do this, is that they have the satellite send the signal over and over again, and they autocorrelate this data. And eventually, the picture emerges, and the noise gets less and less. The more you can send the signal, the better your image gets. This is pretty much what the scientists at CERN did. They had to do their experiment over and over again. But it was a tremendous job. The signal was very weak, and the noise is very strong. So they were doing 40 million to 100 million experiments every second from 2008 to 2012 until they were able to announce to us that they were 95% confident that they had found the Higgs boson. And I guess what I had found out was that they actually went out to 5 sigma, which it means that they were 99.9999% confident that they had seen the signal. I think that when I heard them say 95% confident, I think they were taking into account the fact that the experiment could have some systemic errors in it that weren't related to capturing the signal and correlating the data. Well, now we're later, like in March of 2013, they announced that they have 10 sigma confidence in finding the signal. Well, this is a tremendous achievement, and that's what this video is all about. This was a very difficult problem. We had to have a very precise theory telling us where we were to look for this signal. And then we did a lot of tremendously hard work and invested a lot of money. But the payoff is big to mankind. The payoff in technological gains and the payoff that we're going to see in gains as far as answering some of the deep questions mankind has always faced. Like who are we? And what is our relationship to the universe? Where did the universe come from? Why is there stuff? There's a lot of deep questions that we want to answer, and this is another piece of the puzzle. So please check out some of the other videos. I'm going to deal with some of these philosophical questions.